So appreciate everybody being here, 9 a.m. on the last day of the conference. Today we're going to be going through some data science workflows and using some healthcare data as an example. Throughout this, there are lots of small pieces. Data science in general is tough to keep all of the software connected and working, especially when we're looking at these large workflows. We do have a lot of backup options, so if pieces fail, we should still at least be able to do some visualizations at the end of the workshop. So all of the code for this is up on the GitHub repository, Computational Health ODSC East 17. And we also have a couple of flash drives floating around, so if anybody needs a copy of the sandbox image, just copy that off and feel free to come and exchange off the keys off the side of the podium right here. So the main pieces of software that you would need, VirtualBox, the sandbox image, and then for anybody who is able to, I'm not sure how well the network will stand up for it, but we'll step through this, but installing NiFi or HDF within the sandbox once you get it up and booted will make it so that you can do everything start to finish throughout the workshop tutorial. VirtualBox, if anyone's unfamiliar, link is up there. Basically, it's the Oracle virtualization environment. It is free. This image, you should just be able to go to File, click Import Appliance, and browse to the file that's on that flash drive, and that will import it. And it should just be able to start up. For some computers, it does disconnect the networking cable by default. I'm not real sure why. So if you right-click it and go to Settings, just over in the Network tab, make sure that cable is connected if you get a network not available message once you start the sandbox. All of that will take a little bit of time to copy and import, so I've got some starter slides where we'll go through some background before we actually get into the workshop if anybody's still getting this set up. A couple of other notes within the sandbox, all of the Hadoop services are actually being run as a Docker container. In order to get the message queue to work, you have to do a couple of port changes, and these are all listed on the GitHub site in the README file on the main page. So in VirtualBox, make sure port 6667 is open. You have to unfortunately edit your host file, and then there's a script to download that will restart the Docker container and boot it up with the right ports. But all of this is on the website. Don't feel like you need to do it now. Like I said, we've got data that you can download directly and upload directly to the sandbox without using all of the steps in the workshop, so that we can at least do some visualizations at the end. If everything works, if you pop open sandbox.hortonworks.com or 127.0.0.1 port 8888, this is the image you should get, at which point you can launch the Ambari dashboard, see all of the other Hadoop services that are up and running, or you can browse directly to Ambari at 127.0.0.1 and then port 8080. The username and password is all listed in here, but Raj, RAJ_ops is the username and password for Ambari. For SSH, it will be root and Hadoop, all in lowercase by default, and then it'll prompt you to change it the first time. So while people are kind of going through and getting that set up and running, I'm just going to go through a little bit of background on some of the data science platforms that we use at Yale that are available, a lot of people are using, as well as some background just on healthcare big data, which is really not, historically all that big compared to many other industries. But for Hadoop and Ambari, once you get the sandbox up and running, this is the first view that you'll see. And if anybody is not familiar with it, basically what you've got is a list of all of the core Hadoop services over on the left-hand side, the ability to add services down on the bottom left, and then a little bit of a panel for all of your stats and management statistics. Again, there are a lot of different pieces to Hadoop, and a lot of them work in unison. Some of them you might never use. Over on the right-hand side of this slide, I've just got a list with kind of the key feature of each thing, and the main services that we'll be using today are HDFS for doing data storage, Yarn in the background as our resource manager. Hive and HBase we won't really talk about too much today, but if you're looking for something to do SQL-like queries, you will actually be able to use Hive with the same data set that we import today if that's something that you wanted to try out on your own. Oozie and Zookeeper are really for workflow and coordination between different applications and for the messaging queue, which again kind of run in the background and we won't really talk about too much today. Storm is a great software application for doing big data stream processing. Again, won't talk about in detail today, but I will give you a use case example at the end. Kafka is one of the built-in message queues within the Hadoop platform. That one we will go through in a little bit of detail and is a key component of most big data science workflows that use the Hadoop platform. Ranger, I believe, is installed in the sandbox by default. It's the security module for Hortonworks Hadoop that comes with it. It is a great module, but again, not going to go through it in detail. And then Spark and Zeppelin will go through at the end to actually go through and do some data analysis, make some visualizations on some streaming lab data that we'll set up throughout the workshop. NiFi, if you are able to get that installed, I do have a workflow online you can import, and we'll walk through. But if you can't, we can skip over that to do the analytics later. Once you do have everything up and running, SSH information, if you click that bottom right link, you'll be able to SSH to the container through port 2222, or you can do a web SSH through port 4200. I also have a couple of people here helping up in the front, Will Byron, Tommy Durant, and Carolyn from Hortonworks. So if you have questions, feel free to go grab one of them up in the front corner over here. Otherwise, towards the end of the talk, I'll try to wrap up about 15 or 20 minutes early, so if people want to stick around and work on things, feel free to grab us and we can help out with any technical issues you might run through. Again, I'll post these online so that you've got the details after the conference just to help guide you through getting everything set up. If you want to run, again, everything in the workshop, there's a couple of packages that you need to be able to download in the container itself. The instructions are here and again on the GitHub website. One last time before we move on, I'll just stick up the GitHub addresses, ODSC East17 for the code. And then I've also got, it's about a 1 megabyte compressed 5 megabytes once you unzip it at ODSC East17-data for the other repository. So if you think you might have network issues or just want to get the data that you can upload at the end for analysis, this just has a CSV with about 10,000 lab values that we generated the other day so that you can import those directly into HDFS. And one final housekeeping thing before I start the talk. If you want to try, we'll see how the network does, but if you go to service or actions, add service in Ambari, once you've got it up and running, that'll pop up with a window. Scroll down to NiFi, N-I-F-I, and then just go through all the prompts, ignore all the warnings. Trust me, it's probably fine. And just give that a shot. We'll see if it installs. If not, it'll just roll back. So again, you can always do that at home later if you want to go through the last couple parts of the entire stream processing. So one figure that people, if you've been doing data science, are probably familiar with is this big data landscape, which they try to update about every year and just lists pretty much all of the tools or major software applications that people in data science and data analytics kind of use and touch. And really this is a huge number of applications that in reality none of us know, even at least in detail, more than probably a handful of these applications. Each definitely has strengths, benefits, drawbacks. Everybody has their favorite tool. But the main thing that we want to go through today with the workshop is really trying to figure out how can you go through this entire landscape of a million different software applications and find a core set of applications that you can use to really put in production-grade workflows within your organization. And we'll try to go through that. We'll do some code throughout the workshop as well. One difficult problem we often run into as data scientists, engineers, and analysts is that big data projects often don't have tons of detail, at least at the beginning. So, you'll have a new data stream or you'll have a lot of old data, and somebody in your enterprise wants to move that into your big data platform or wants to do analytics because machine learning is definitely going to solve all of our problems. So how do we actually do that step two, though, is a big problem that we haven't really we don't always flush out from the beginning of a data science project. So we've got data set. We know we want to do analytics. We don't necessarily know what kind, which makes it tough to really say, well, how do we model the data? How do we make sure it's accessible? And how do we make sure that our systems can support the scale of analytics that we want to do? And tools like Hadoop, while fantastic, I think have actually kind of accentuated the step two problem of we can move in unstructured data. We don't need to have a data model. We don't need to have specific data formats. We can suck everything in, put it on the drive, and it's there and ready to go later. The problem is that a lot of times we end up with data graveyards rather than anything that we can actually do data analysis with downstream. So it makes it kind of a problem for how do we manage these really large data sets, and healthcare is no exception to this. So even with a couple of very popular initiatives that a lot of major academic institutions are working on, the Precision Medicine Initiative or All of Us program, as well as Cancer Moonshot, these different studies are taking that big data approach of let's collect a lot of data, let's sequence everybody, let's just sequence every tumor, and we'll figure out the analytics later. So the main thing is that we can get the data, Somebody will be smart later and figure out what to do with it. And again, none of us, I think, would complain about having more data and more robust data. The problem is that without that step 2, it makes it definitely tougher for us to figure out how to implement our workflows. So as an architect or developer, data scientist, what do you do when there isn't a step 2? And just as a couple of best practices that we'd have definitely try to follow as we pull in our data sets is obtain sample data whenever you can. Being able to see some of the data up front rather than just accepting any file is definitely helpful. If you're able to, at least try to explore the data in some level of detail. Find out if there's some structured elements you can get, even if it's just a timestamp or a source system, something that you can at least identify that by later on. When you do capture and store that data, try to create these reusable workflows, and we'll go through that today so that you don't have to reprogram everything from scratch with every new data set that you might be pulling in. And when possible, even though you might not be able to do detailed analysis, at least try to extract some structured elements, again, when you can do that from your data set. So timestamps, user IDs, anything you might be able to index or filter on as you go through those steps when analysis questions come up later on in your workflow. So today we'll go through 3 different healthcare use cases. One is the workshop use case in a little bit more detail, which will be looking at clinical laboratory informatics and streaming laboratory data. And then towards the end, I'm just going to talk about a couple of other projects where we've reused several of the same components for doing continuous patient monitoring within our health system, as well as for image analysis and deep learning. So we'll go through kind of the workshop use case, step through all of the steps of making those workflows, and then look at a couple of other use cases where we've implemented them in production. And really the goal here for today is that even though you might not go through and write it, is that you'll at least see the process of being able to review some data, generate data sets, ingest something either from file or from a streaming source, where to store that within the Hadoop platform, some of the basic tools you can use for data transformation, and then we'll use some Zeppelin notebooks and Spark at the end to visualize and explore that data that we generate and import. The one thing that I would encourage all of you to do is really, again, from that big set of thousands and thousands of applications, find your personalized data science toolbox that really works for you and within your business setting. So find the tools that you think you can learn, that you can implement for each step of the process. And again, we'll go through that as we step through. Before I move into the healthcare system stuff, does anybody have any questions? Or we've got some flash drives up here again if anyone needs the sandbox image. Nothing so far? Great. Okay, so data flow within healthcare, like many other places, is complex. We always argue that we're more complex. Whether that's true or not, I'm not sure. But when we look at all of the different source systems that we run into, we do have a lot of vendors and a lot of interoperability issues. So looking at your physician who might be seeing the patient, ordering a lab, writing a prescription, most of their interaction is going to be through the electronic health record. For EHRs, there are many different vendors. There's 5 major vendors, lots of smaller ones that are scattered throughout the industry. Because of all of that vendor, the very large vendor set, there are some healthcare standard data formats, but most things go through what we call an integration engine. So when an order is placed for a lab or a medication, that order gets sent from the EHR to an integration engine, at which point it goes to something like the laboratory information system or the pharmacy system. If it's something that needs to be run on an instrument, so if we're doing a CBC that needs to be run on an analyzer, that order will then go from our LIS to something that we call middleware, because most LIS systems do not talk to instruments. Why would they? Once it hits the middleware, sometimes the instrument has middleware of its own, at which point you can finally put your sample on the device and get an answer back out, at which point that data has to flow all the way back out through all of these systems again. So trying to actually integrate these is definitely a challenge, and we do have some clinical data and enterprise data warehouses that we run within all of our health systems. The problem is that most of those come off of the EHR and come at a nightly or weekly export. So by the time you're doing analytics, your data is already in some circumstances quite old, depending on what your question is. So what we've implemented at Yale and other places are adopting or have adopted similar approaches is that from the integration engines and from the enterprise data warehouses, we actually export those into a data lake or data science environment. And for us, we do a combination of Hadoop and Elasticsearch for our environment, which has all of the components listed down on the bottom right of this slide. So with that, the goal again is that we'll now walk through kind of a use case of generating laboratory data from that top level, passing it down, getting a result back, and into something that we can actually analyze, look at turnaround time, order volumes, and so on for some laboratory data. Like I said, a problem with our current enterprise data warehouse is it's not real time, and the two of the very specific use cases that we ran into, which is why we started developing this application in-house, one of them is quality control. So, one thing that we see is when we run lab samples, if we took a sample of blood from somebody here, got something like a white blood cell count, so the cells that fight disease, and ran that on our instrument, we got a value out. If we took your sample back to the front of the line and ran it again, we would probably get a slightly different number just because of differences in the sample, instrument changes, even things like humidity can alter those values. So we have to run a lot of standards to make sure that the numbers that we get back to physicians out of the laboratory are valid and accurate for making a clinical decision. The problem is that right now we run those often at like 2, 4, 6-hour periods, which means that we can make some errors in between and have to correct results every now and then. Doesn't happen often, but when it does, it's a little bit of a problem. So if we have a real-time data stream, we can start using moving averages of actual patient samples to identify those issues earlier and try to prevent those mistakes. And then the other thing that we wanted to look at was actually starting to do some business intelligence within the laboratory. And again, rather than needing to wait a day or a week, can we actually see what is our laboratory volume or what's our draw volume from our remote draw stations? Which labs are we doing high volumes of, low volumes of? Are we running behind? So one question that often comes up, we actually contract sometimes to our different departments. So like the emergency department, we will say we will turn around stat labs for something like a heart attack within a certain time frame. So can we actually get an interface to see what those turnaround times are and make sure that we're delivering on those promises? To actually answer these, we don't actually need every piece of data out of the EHR. It's actually a fairly small subset. So, the lab test name, the time of collection, the time of result, and the order location really gets us most of what we need. And fortunately, that interface engine creates what we call an HL7 feed that we can ingest those data points from, and we'll go through that in a little bit more detail in a couple of slides. So just to look at what we'll actually build in the workshop, we'll start off by making a data generator, an HL7 data generator in Python. So if you don't have a Jupyter or Python installed on your host, that would be good to have ready if you want to go through all of the steps. We'll use Kafka as our messaging queue to pull data into the Hadoop environment. We will then use NiFi for doing some stream processing, and we do have some Python scripts that we can replace that with in case people don't have NiFi up and running. We'll store that data to HDFS for the purposes of this workshop, and then we'll use Zeppelin and Spark to analyze that at the end. So again, kind of going through this entire workflow, looking at each of the components, and we'll hope that VirtualBox and Jupyter play nice on my laptop for the duration to show you guys. So problem number one in healthcare data science in general, and this is for every data set, is finding sample data is problematic. So trying to find healthcare data that you can actually look at, play in any appropriate volume is very difficult due to privacy regulations and people just not taking the time to make it. In-house, we are able to actually pull some of this data from our test systems, but for most vendors that we work with or startups that are trying to get into healthcare, those aren't data sets that we can usually share, which makes it, again, tough to really break into healthcare as a data science industry, both for those of us in it as well as people outside who are trying to move into the field. So trying to do that, if you can generate the data is definitely beneficial, which we'll do for the first step of this. The other issue with our healthcare data streams is that they are extremely messy. I don't know if anybody's ever actually worked with HL7 or has seen the new Fire spec that they've been putting out, but these are not simple specifications, and the other issue is that they are often infinitely extensible, which means that they're a little bit less of a standard when you can do anything you want to it. As we pull data, actual real data from vendor systems, it's not a problem with generated data, but many of our instruments, the middlewares, they don't actually always follow the exact specification. So when you're pulling these, if you actually look at a production or a test system where you're looking at real devices or real vendor software, just be prepared that your standards may not always actually be standard when they come out of those devices. And then the last thing is that as you move between facilities, one thing to keep in mind is that a white blood cell count at Yale, we might call it by a slightly different word than at another healthcare institution. So one place might call it WBC, we might call it white cell count, somebody might have white blood cell count. While there are some standard ontologies and naming schemes, not everybody implements them in these data fields or within their EHRs, so it's definitely a challenge to integrate data across institutions. So standards exist, not always followed, and not always implemented completely. Just as an example of the messages that we'll be creating today, so that HL7 generator, this is basically what HL7 looks like. So we've got some IDs over on the left which tell you what type of field this is. So this is the MSH, this is a patient ID, this is an OBR, OBX, and an NTE, which is note. The pipes are the delimiters for the different fields. They also use carets and a host of other characters as separators between fields and subcomponents. There's a lot of detail on the CorePoint Health website, not related to us at all, but it's definitely a very good resource if anyone wants more information about HL7 or Health Level 7. So MSH, just to walk through a couple of these that we'll be using today, that is the header field, which includes things like the message timestamp, so when was this message generated. PID is the patient information. We won't have any actual patient information in our messages, but this is where names, addresses, insurance information, identifiers would be stuck in actual messages. The OBR is the actual order. So for this HL7 message, this was an order for an upper respiratory culture, and then the source was the throat. And then the OBX is the result and then associated notes. So the result of this is that there was a positive culture for Moraxella with heavy growth, and it was beta-lactamase positive. So you don't always need to know all the details, but those are kind of the core or key points of each of those messages. So with that, I'll stop talking for a little bit, and we'll get over to actually doing a little bit of code now for the workshop piece. Again, these are on the GitHub site if you haven't seen it already, but if you want to run the Jupyter notebooks, the main packages that you need would be matplotlib and pandas. And then if you want to be able to send this to Kafka, you'll need to pip install the Kafka package as well. The code for this is all in the GitHub repo, or if you want to just kind of copy it along with or write your own, you're more than welcome to as well. So with that, if anybody has questions, feel free to come up, and I'll get this notebook pulled up so that we can actually kind of start walking through it. Okay, so the first thing that we're going to look at is just kind of exploring some laboratory data. So, it decided to turn off on me. There we go. Thank you. So the first thing that we'll do is explore some of the laboratory data that we actually had to see, what would be good data to generate. So the thing that we sometimes run into is that just generating random values isn't always helpful for some of the algorithms that we want to test. And just to see kind of an example of that, if we go through, so sodium is one of the values that we do for what we call a basic metabolic panel, so one of the electrolytes that's in the blood. And the physiologic range for sodium is quite wide, so 125 to 155 with maybe a little bit more. The problem is that our normal range is really 135 to 45, so 95% of people will fall within a very, very narrow range of sodium values, and if you get outside of that, you will likely be in the ER or ICU very quickly. So if we go through and use kind of some of the standard Python tools to go through and create random values, so here what we're doing is creating a new array, setting our min and max, so this is our physiologic range of 125 to 155, and then we're just going to go through and create 3,000 random samples. And when we plot those out, we can see that Python does a great job of giving us a fairly even count of values ranging from 125 to 155. The problem for a lot of our tools that we would actually want to look at this in the healthcare setting is that this is not, if we looked at, say, 1,000 or 5,000 or 10,000 patients, this is not the distribution that we would see. We would not see 20% of our patients having a sodium of 125, otherwise our hospital would be much, much busier. So there are, fortunately, some really good tools, and the point of this is I just wanted to kind of point out that NumPy actually has really nice tools built in for generating normal distributions. So given a mean and a standard deviation, actually being able to generate random values, semi-random values, that fall within that normal distribution or normal range. So instead of setting the min and max, and we've got these values out there, so we actually ran and went through and found out what is the mean value from several months worth of our in-house testing at Yale New Haven. So the values that you see up here are averages based off of large numbers of patients or large numbers of samples. So our mean for the sodium was 139.594 with a standard deviation of 4.475. And if we go through and use NumPy random normal rather than random, you can set your mean, your standard deviation, and the number of samples you want. And we can see now that we actually get something that would be more realistic of a patient population. So most of our samples distributed between 135 and 145, with some samples falling outside of that normal range. We can go through and do similar things. So in some of the other code samples, you'll see that we've added on the potassiums, chlorides, other components of our basic metabolic panel. And again, we can go through and distribute those values so that we see everything falling really within what's more typical of our patient populations. And when we're looking at testing things like moving averages, being able to generate ranges like this is very important so that we can actually trigger errors that should pull up and alert our instruments that a problem is happening. If we wanted to do something like skew our distribution, this next cell here, so this line, what I've done here is actually set a low error rate and a high error rate of 5% and 1%. So when we go through and look at this, I've just got a couple of plots to kind of show the differences. But as we go through, the same as we did in that first step. So we're going to create an array to hold our distribution. We're going to generate a range of 3,000 values. And for each of those, we're just going to generate an actual semi-random number from NumPy. And that number, when you do this, will be between 0 and 1. So what we say here is, if that random number is less than our low error rate, let's generate something that's between 2 and 3 standard deviations below the mean. If we generate something that's above our high error rate, so 5% or 1%, let's generate something that's 2 to 3 times above the mean. So this takes our normal distribution and just skews it a little bit. And we can see kind of, this is an example with 5 and 1. If we go through and change this to something like 15, that skew will become much more apparent. So just try to keep in mind what these kind of look like. So we've got a few bars that are picking up here on the ends, but most of it's still centered. And first error is always good. Let me just run through these other ones so that I get all my other variables created quick. So here we can see now that we've skewed that distribution more. We've got many more that are on that negative side. So again, something like moving averages, by putting these into your data streaming application, you can actually introduce that skew to alert something like a machine learning algorithm or try to actually trigger that as a positive control. So it's nice to be able to work with your data sets and get something, again, from that data generator side in your toolkit that can generate things that will actually be useful later on for testing things like advanced analytics. Okay, so we've kind of looked at the data and what comes out of it. The next big thing is actually trying to generate something in an HL7 message. So if you go into the generation and 3 generator PyKafka folder within the GitHub repo and the Kafka data generator normal distribution notebook, this one takes a very similar approach to what we were doing. There is one file that gets imported that's called observation, and we'll look at that just really quickly to show you what that one does. But that basically will grab and say, I want to generate a random basic metabolic panel, or I want to generate a random CBC, and we'll give some random values for that, and just makes it a little bit easier to step through the code. So here's that observation file that gets imported. So our comprehensive metabolic panel, this is actually more of a basic metabolic panel here, but we're missing a few components. So basic metabolic panel has most of our electrolytes, so sodium, potassium, chloride, bicarb, BUN and creatinine, which are markers of renal function, and then glucose, which is mostly for people who would have diabetes that would be concerned. The other one that we've got in here is a CBC, so just defining our components again. Hemoglobin, hematocrit, white cell count, and platelet are the main components of our core CBC. All this file does is go through each of those components, and we'll generate a random value. And again, we've got some nice values that will actually fall within normal physiologic ranges for most of these patients. So if this is something of interest for you guys later on, these numbers should actually reflect what's seen in human physiology. The main core point of this code is that whenever this is called, it will generate, basically, it'll pick one of those from up top, generate the random values, as well as some random timestamps that we can use for looking at things like turnaround time between our different specimens. Okay. So the next piece is going to actually be trying to get this generated into HL7 and then loading this into the Kafka queue. So before I actually step through the code here, just so that people have it created on their workstations in case they want to, in case you wanted to do it yourself, you will want to SSH over to your container. So that should be on localhost 2222. Root, and if you haven't logged in yet, the password will be Hadoop, and it'll prompt you to change it on the first time. If it complains about your new password, it does require a fairly significant password to actually get through it. So this is our Hadoop container, and so this should be the same thing that everybody else is running. The only exception is I've got a couple of Python files that we can use to kind of get to data later for ourselves. So Kafka, the main thing that you need to remember is that if you want to start a Kafka queue, there are two ways to create them. If it's configured to create a queue on demand, that will happen as soon as you push a message to Kafka. That is the case by default, but it's always a decent practice to actually go through and create the queue yourself. So to do that, you just need to change to the Kafka directory, which is USR, HTTP, current, and then Kafka broker. And then if you change into the bin directory of that, you'll see a lot of Kafka management scripts. So user HTTP, current Kafka broker, and bin. From within there, these all manage Kafka as well as have some command line clients for either pushing data to the queue or pulling data out of the queue. If we look at the Kafka topic script, and the only main thing that we need to do is Zookeeper. So you have to list your Zookeeper address, which will be localhost and 2181. And then we'll say list, which should give us a list of topics, assuming that I typed that all in right from memory. So we can see here that we've got a couple of pre-created database queues that are being used by Hadoop itself, and then test 1 and test 5, which are some queues that I had created to play with. If you change from list to create, and then add topic, the topic that you'll want to match the instructions I currently have is test 1. We're going to do a different one up on mine just because that's already created. The other key things that you need to put in are your partitions, which should match the number of nodes that are running Kafka, or your number of brokers, which here will be 1. Replication, which will be 1, so that's how many copies you want stored. And I think that's it. We'll see if it gives me a complaint. There we go. So once you type those in, that should be create your topic, at which point you will be ready to go. If you want to test and make sure it's working, you can do Kafka console consumer, your Zookeeper address again, and the topic that you want to connect to. And that should pop up with a message complaining that it's using something that may be deprecated in the near future. And then it should connect and basically have your connection information. So if you see this message, this means that you were able to create your topic, connect to Kafka, and everything should be set. If for some reason it's complaining that Kafka is not available, go back to Ambari, go to the Kafka tab, and make sure that the service is listed as started. If not, service actions and start from the top right corner. Okay, so now that we've got our topic created, we can come back to our code, and we should actually start to see HL7 streaming here in the next minute or so. So the main things that we've got here in terms of configuration, our new line, just because we need that, our sleep is basically how long we're going to pause before creating another random message. So for here, we've got a sleep time of 2, and per iteration, we're going to generate 50 HL7 messages to send along to our message queue. You do need to list your Kafka brokers, so sandbox.hortonworks.com, 6667, and your topic should be whatever topic you just created there. This uses a Kafka library that's part of, you can install by pip or pip, I believe. I don't think Conda actually has it listed, but works very well as long as you're not in a secure or Kerberized environment. As you go through this, this then just basically infinite loops us at every 2 seconds will generate a new value. So let's get that started and just make sure that we're getting our HL7 to come out the other end. And here we can see we're just printing out HL7 messages down below as they come across. And we've got lots of basically incomprehensible text, which is what you would expect from an HL7 feed, so that is perfect. If you left your console consumer on, you should see those messages coming back across. So this is basically just running in the terminal, and every time a message is sent out of our Python script, this is coming into Kafka and then just printing out on the terminal, so we know everything is in, working, and coming across nicely, which if it didn't work for you on the first try, don't worry. This takes about 10 times to really get and work well without causing a bunch of errors on the way. If you just want to test it out and see if Kafka's working, so let's say that you're having some issues with getting Jupyter running or don't have that available, from that data GitHub repository, I do have a CSV file. It won't generate the HL7, but you can upload the CSV if you want. So after you extract it, you should get this generated data.csv. And if you just want to feed it in to see how it works, we can do 2 different windows here and generate actually a Kafka producer and a consumer both from the command line to make sure that it's working. Okay, so on this side, let's start our Kafka broker again, or our consumer, our listener. And let's use a different topic just so that we don't get messages of different types coming across. On the other window, what we're actually going to do is go back to that same place and get there's also a producer. And if you ever want to see what the different parameters are, what you might need, if you just type in the actual script name and hit enter, that will print off your list of parameters for any particular command in this file. And I think that should work for us if you want to see more of that command. Basically what we're going to do, so the Kafka console producer basically takes one line, and for each line that you input from standard in, will generate a message to the message queue. So what we're going to do is just feed in our CSV file as our standard in, which, if that's typed right, Kafka broker. Just run it without that so I can see which one it wants me to use instead. Broker list, so close. So there you can see we've read in our CSV file and just dumped it out on the other side. So if you just want to play with Kafka to make sure it's working, it's a quick and easy way just to get into the interface and get stuff streaming across the message queue. Okay, so we've got our data feeding in, and that'll just keep sending 50 messages every 2 seconds in the background for us as we get to the next step here. So one note looking at our laboratory data, again, we often have many different tests. Each of these tests often comes with components that we already saw. So our CBC, which is a panel, comes with many separate components, as do our basic and comprehensive panels. Each of these has different normal ranges which we generate. And again, generating good test data sometimes requires more than a random number generator if you want to reflect what actually might be coming out of production systems. This is just kind of, again, I was actually supposed to go through these slides before I jumped into code, but I was getting antsy to type something. But looking at our different ingest tools, if we looked at what we might use to architect some of these data science pipelines, if we look at just general categories, and there's a lot of semantics that goes into whether this is appropriate categorization, so please ignore any complaints there. But for looking at data ingest, we have things like Scoop and HDF, which really do good at pulling data into a cluster. You can use things like Storm and Spark for doing that as well, but these are two of the major tools for that. The other thing that kind of falls into that category, which is Kafka, a messaging queue. One other that we use, it's not technically part of Hadoop, is RabbitMQ, but works very well as a messaging queue system as well. For processing, Storm, HDF, and Spark are three of the main applications that people look at. Storage, HDFS, Elasticsearch, HBase, and then for data analysis, Spark, Elastic, Python, and a host of others that aren't listed here. So going back to that data ingest, again, this is here mostly for reference and notes in case anybody wants it afterwards. I'll get this posted online, but for creating and setting up your Kafka queue. This is for starting up your Kafka producer. And then the next piece is going to be moving into our data load. So now that we've got our data being generated, the next thing is going to be saying, okay, we've got it. How do we actually get it into the cluster, into something that we could actually store and analyze later on? And for this, again, big things that we want to try to take along with us is we don't need that whole HL7 message. We may store it as a full message so that we can reparse it later for getting other data out. But the main things that we need now are our timestamps, our values, and our component names to pull out of those messages. So if you have NiFi installed, the workflow that I'm going to pull up here is actually pre-created in the, I'll show you where the directory is. You can actually upload that to NiFi and have the workflow pop up for you. There's also a Python script that can do the similar thing. So it can basically take that and push it over to HDFS in case NiFi isn't up and running for you. So just looking at the directory quick to show you where all of that code is. So within the ODSC E17 directory, there's one ingestion, there's NiFi, and then in Python CLI. And we're just going to look at the Python one quick first, just so that you can see that and get it up and running if you want to. So for this one does require you to have that Kafka pip library installed in the container, so sshn and pip install Kafka if you haven't done that already. The first two here just set up the Kafka client, much like we did in the producer or from the command line. And then what we're going to do is say that for every message that comes across our Kafka client, we're going to append that message value to our queue. And then we're going to extract out the main things that we need from our message. So the main things that we're looking at is the message timestamp. So what time was the message generated? And that's in the, this is basically saying if the line starts with MSH, so that first field is our line indicator, grab out the timestamp for the message. If it's the OBX, that's going to be the actual result. So each of those are the result lines. And then down towards the bottom is the OBR, which is the order. So that's the time of order. And if we wanted to look at turnaround time, so how long does it take us to actually run or send out the lab result, that's going to be taking the timestamp from OBX and subtracting the order, the OBR timestamp from down here. So we'll get into that in a little bit later, but those are the reasons that we grabbed all of those fields. One thing to remember is that for these panels, there are multiple OBX messages per HL7. So that can mean that if somebody ordered a CBC, there's going to be multiple results in that same message. So you can see when we append here, we're actually overwriting data within the overall dictionary that we create. And then we're just adding a copy of it to our list so that we can maintain or basically denormalize the result files that are coming out. After that, you should also have installed the HDFS, so pip install HDFS, which is on the GitHub instructions. And when you do that, we can then just basically, just as if we were writing a file to disk using Python, we can say with our HDFS client, open a path up on HDFS and write these files out as HL7 messages. So if you run that from the container itself, so if you SSH in, put this code in, basically that should just start writing data to the HDFS file system. You may need to play with your path. If you need an easy one that you don't have to create any directories, just write to /tmp, should have all the permissions you need to get files and data flowing out. So that one will get you up and running, but the more interesting one is actually running through NiFi. And this will actually go through in a little bit more detail, just because NiFi has a lot of different pieces to it. I'm not sure if there were any other talks on NiFi yet. This is a tool that was actually created by the NSA and then transitioned in the open source community a number of years ago. But its main thing is doing big data stream processing. So how do we ingest data, how do we transform it, and then get it into a data source for us to use later on. And we'll go through some of this interface, but really just getting fluent in it takes a long time, not necessarily a long time, but just takes some time playing with the interface to become really familiar with where all of the different tools are. So the first thing that I usually start with on any NiFi workflow, which we call right here, is dropping in a process group, and that's this middle button, and that basically just adds on a folder equivalent that you can drop other processors into. And let's zoom out a little bit since we're on a slightly low resolution. So when you double-click that workflow, so if we double-click this test processor group, basically it just opens up a blank screen where we can add on more processors. So the processors are the main driving part of NiFi. So the processors do everything that if you were writing in Storm or if you were doing in Python, you would largely be writing by hand or configuring by hand. So if we look at this, there's a great filter that we can basically say, our first step of this pipeline is that we need to pull our data in from our Kafka queue. So we can type in Kafka, see that there is a consume Kafka processor, and that will drop the processor onto this for us. Once the processor's there, again, this is very UI-based for being able to do configuration. So we can right-click, pick Configure, and now we've got 4 different tabs. So the first one is the general settings for the processor, which includes things like how long to wait if there's errors or configuration errors so that it doesn't just tie up processing by generating those errors over and over again. There is scheduling, which depending on the processor will be either timer-driven or cron-driven. So you can either say run this processor once every 3 seconds or on demand, and then you can set how many concurrent tasks. So if you've got a very big data stream coming in from Kafka, you might want 2 processors pulling in that data at once rather than leaving it to 1. And then the main settings is the properties tab, and this is where we'll get into the bulk of doing everything. If you've got NiFi up and running and you want the pre-created workflow so that you don't have to type all of this by hand, in that ODSC East 17 ingestion NiFi, this lab data processor has all the pre-created workflow that you can import, and I can show you where that is real quick. So up in the top right, if you click those 3 little arrows and do templates, and, oh, I moved it. Carolyn, do you know where the import is on this one? For importing a template?
Oh, go to the top.
Oh. The too far left? This one? If it's in an XML file, like getting it into NiFi?
Yeah,
lower left.
The one with the little...
Create? Grayed out. We'll get to it later. So you can import it if you need to. There it is. Now it works. So make sure you're not clicked on anything. So down in the bottom right, I mostly create them. I don't have to upload them. So there's the upload button. If you browse to your template and upload it, once it's uploaded, then you can basically just drag this template down, say that you want the lab data processor, and that will create your whole workflow that we'll go through and build right now. Okay. So going back to our consume Kafka properties, one thing to remember about Kafka is that it typically binds to a host name in most configurations. So while localhost is often typed in by default, you usually need your host name if you actually want it to work. So sandbox.hortonworks.com, and the default port for the HTTP distribution of this is 6667 for the plain text endpoint. So the other things that we need to fill in is our topic name, which in this case for mine was test1. If you named it something else, just put in your other name there. The group ID is something that ends up getting stored in Zookeeper to remember what your offset is. So Kafka works really based off of your consumers. So Kafka doesn't remember what the last message that read was. It just knows that there's messages in queue and it maintains them for some amount of time. The default, I believe, is 3 days. So when you push a message to Kafka, it stays in Kafka for 3 days, and it's up to your consumer to know which offset to start at if there was a failure or you want to start fresh. So giving this a group ID just keeps that so that if you restart your NiFi workflow, it will pick up and resume reading in that last message if those settings are configured appropriately. So that plays into this offset reset, which can be either earliest, so as far back as your last offset, or the most recent message and basically ignoring the last offset that was read. Okay, so once we have those in, that's going to create the first step of our workflow, and that's actually ready to read in data from Kafka. If you see this little orange exclamation, that means that there's some property that isn't set or some data flow that hasn't been specified. So all of these processors need their data to go somewhere. So you can see that if you go back to your configure processor and on the settings tab, this processor only has a success. So basically we need to say that every message that has a successful status, we can either automatically terminate that and say just discard the message, which is what that does, or we need to point it somewhere. So let's uncheck this. And because there's a bunch of config, I'm just going to jump over to our created one here and step through. So the next one that we're going to do is actually execute script, which is going to parse out our HL7. Now there is an actual HL7 parser, this extract HL7 attributes and route HL7 message within NiFi. These processors are actually very good. The downside is that they expect fairly pristine HL7, and because we don't have all of our fields filled in the generator, most of our HL7 messages using these default processors will actually be rejected, so we're just going to use a small Python script to do that instead. But for actual production, those HL7 processors, while they have a little bit of speed issue, or they used to in past versions, work fairly well for parsing data. So if we right-click our consume Kafka processor and hit start, we should shortly here, this works on a timer method, so we don't see this necessarily update this interface in real time, even though stuff is already happening. But within a second, we can see that we've already now queued up 12,285 messages and 6.6 megabytes of data. It might be a little bit hard to see on the screen, but you can see that this bar turned red. And what that means is that we've now read in so many messages that to make sure that we don't use up all of our memory and everything else, and we're actually just going to turn this off. But all of these data flows, so if you drag out, you can create these data flows which actually move the messages across. These also have configuration settings where you can basically set back pressure. So you can say once I get to a specific number of objects, so this is defaulting to I think that's 10,000, or a specific amount of data, 1 gigabyte, apply back pressure so that you don't keep reading just more and more data. So that basically signals that you've got an issue somewhere. Either you need additional processors to keep up with the speed of your data, you've got an error in your pipeline, but for some reason messages are being queued up, which means that you've got something to fix. And there's actually a reporting framework in here where you can send alerts if you end up having a lot of messages in queue or in your backlog. So we've got our HL7 messages in. The other really nice thing about NiFi is it makes it very easy to actually look at what do your messages look like. So something that in Storm is actually fairly difficult to debug is if you do pre and post, unless you've got a lot of really local stuff running in Storm, it's kind of tough to see is your code working as expected. In NiFi, if you actually right-click that queue line and list queue, view details, you can actually see the exact message that's in the queue. And if we click view, we can see here we've actually got our nice, pretty HL7 message that came in from our data generator. So again, this makes this tool very nice for debugging these workflows and for making it so you don't have to code everything by hand and get into all of the terrible details of what is big data processing. And really speeds it along. So being able to do this really helps in terms of getting these pipelines created and getting the processing you need done. So the execute script processor basically allows you to do ad hoc scripts for processors that might not exist within NiFi itself. So NiFi does let you build custom processors in Java that you can compile and upload, but if you've got a fairly small processing step and you want to be able to adjust it, it may be easier actually just to write code yourself and not actually compile it into a formal NiFi processor. To do that, you can use Python, Lua, Groovy, Ruby. And once you make your script, you can either put that on your host and set the path using the script file parameter, or you can actually paste the script itself into the script body parameter, which is what I've done here. And if you want to see the details of that script, it's basically the equivalent of Kafka to HDFS, but just with the NiFi framework around it. So if we look at HL7 parser, this is the same code that's pasted in there. To do a custom NiFi processor or script that does this, there are a few things that you need to import. These are all installed with NiFi, so you don't have to pip or conda install anything. But once these packages are installed, you do this PyStream callback, define a couple of functions that are required, at which point this line basically reads in the flow file from the prior processor. So doing this basically takes the top file off of the message queue, converts it to a string, and puts it in our HL7 message variable. After that, this is the exact same thing that's happening for our Kafka to HDFS. So we're just parsing out the HL7 messages that we need, copying them onto the array, and then for each message that we have, we are making a new flow file. So this output stream.write basically writes this back out as a JSON file. So I'm doing JSON for a couple of reasons that you'll see later rather than just straight to like CSV. But basically, once we get here, we are producing JSON, making an array, and sending that out to the next processor. So assuming I haven't made too many mistakes since last night when I was playing with this and started generating all sorts of terrible errors, version control is always a good thing. When we run this, we should see that those 12,000 messages should all come down here, and we should actually have a few more because we should be denormalizing. Those are coming across as a JSON array. So there you can see we started processing. So our red bar, or number up on top, is going down while this other queue is building up. And if we pull up our list queue here, we should be able to see, again, the exact message that came out of our script processor. So now we went from HL7 to something that's more human and machine readable, so JSON. And we've got our method, which what is basically our instrument type that we're faking results from, our result and requesting timestamps, the component, the units that our value is measured in, a couple of other timestamps, and then the actual value, which for some reason is a string right now, but we'll pretend that's not happening. It probably won't impact anything later on. We can update it if we need to. So we've got our data coming through. We don't have any errors. If there's an error for a specific processor, you'll get a little red box up in the top right that looks like this one. And if you hover over, it'll give you the list of errors. This is just saying it can't do reporting metrics. But if a processor has an error, you'll see the same thing. So now that we've got our JSON array, what we want to do is convert this to a CSV file so that we can actually read this into other things and do analytics later. You could write directly JSON to HDFS and do analytics as well, but I just wanted to go through a few more processors so that you could see what they do. So the split JSON, basically you can give it a path. If you do $.* that means split at the root element. If you actually gave this a path, it would split an array that's actually a field within the JSON document itself. So this one actually should match the number from above, and when we run split JSON, that should now denormalize it so that we get a message for every component rather than a message for every order. So every CBC should make 4 different results for us now, and those should start piling up in the split queue. After that, we have JSON, again, that we could write directly to HDFS. But what we're going to do is convert this into a CSV so that we match our other data that we generated on the fly. For people who don't have NiFi or don't want to get it up and running. This processor basically takes and says that if you give it a field name in your JSON document, it will add this value on the right. So NiFi has its own expression language, which we won't go into too many details of. But what this basically says is for the component field in JSON, set that as an attribute value. So if component is white cell count, make that an attribute value in the NiFi flow file. And that may seem weird because it is, but the reason that we're doing it is now that we're going to use this replace text processor and basically say for each of those attributes, so using this language, you can basically do $, curly bracket, and attribute name. And we're basically just going to stick all of those attributes and mock up a CSV. So it's the timestamp, comma, the next timestamp, and so on. And one note is that if you want to combine these into a single file, to get a new line at the end when you merge these together, you have to do this $ curly bracket literal \n. Otherwise, it just ignores the backslash and just puts an n at the end of the line and puts everything on one line, which is not helpful. So literal \n if you want to do new lines when you append this in HDFS. So we can see all of our stuff is coming through. We've got some back pressure here from stuff that's queued up. We're going to start our replace text to start making our CSV. And then the last thing is that we're going to do is give it a file name using this update attribute command. So mini small files in HDFS, if people have worked with it before, is a bad thing, so don't put lots of 1 kilobyte files in your HDFS system if you can avoid it. What this does is it basically generates a file name based off of the current date and time, so minute, date, or month, day, year, hour, minute. And you can set this up however you want. This is just for demonstration purposes. For some of our high volume data streams, we basically divide out by hour or when we hit exactly 128 megs. But for this, we're just going to split up a new file every minute. And when that passes to HDFS, that's going to write it to our HDFS file system. And just so that we can see that happening, if you're in Ambari and click those 4 or 9 little boxes up in the top right, you can do Files View, which will basically pop up a viewer of your HDFS file system. I'm also going to turn off our data generator since we should have enough to play with at this point. So here I've just created a directory called lab data and NiFi, which you'll have to create if you want this to run completely appropriately. There's a couple of these in here from last night, I believe. So let's just delete those quick. Okay, so we can see that we've got an empty directory. And if we come back to our NiFi flow and start HDFS, we should start seeing files created. So we've got our CSV. And if we open, we should see the same data that we saw from before. So we've now got a CSV that has all of our laboratory data, our timestamps, our values, so we're now ready for analysis. So all of that code to make a couple of graphs, totally worth it. So the last thing that we'll do now is kind of go through a little bit of Zeppelin, and I'm skipping over a little bit of the presentation stuff so we can go through this and try to answer questions if anyone has anything here towards the end. 10:30. What time are we actually done at? 8:30. This is also, the Zeppelin notebook is also present here if you don't want to create it by yourself. If you go to ODSC East and Visualization 1, there's this Zeppelin Lab Data Notebook, which will have all of the code that I'm using that you can, again, import directly into Zeppelin. If you don't have Zeppelin running yet, from the Ambari interface, if you scroll down to the bottom left, Zeppelin Notebook. If it's not in the started state, service actions start, and then quick links and Zeppelin UI will pop that open to the right port and everything for you. If you need to import the note right here, just browse to the folder, upload that file, and you'll be set to go. So Zeppelin, if people aren't familiar with it, is basically just another notebooking platform, so similar to Jupyter, but really more focused on doing Spark than necessarily Python. So you can install other interpreters, but Spark and Spark SQL are a couple of the big ones that we end up using it for. So just to step through what this code is doing, basically the first thing we're going to do is set up a class for our lab result that has all the timestamps so that we can specify the data types. If you were loading JSON, you wouldn't necessarily need to do this, but as a CSV, we need to. We're also going to specify our date format. So the HL7 date format specification, much like the rest of HL7, is a little bit tricky. So it's year, month, day, no dashes, no colons, no T's, hour, minute, second, and then you can include the time zone at the end if you want. But has to be a string, has to be that format for valid HL7. To do some of our math, it's a little bit easier if we are in timestamp format. So we're going to include that simple date format parameter, which comes from the Java text simple date format library, so that we can convert our string timestamps into seconds. The first time you run one of your notebooks, so up here we're specifying that we want to use Spark 2, which is the default Spark running on the sandbox. The first one that you run will take a few seconds to run and load as everything kind of gets spun up and processed the first time. I was running into some issues. The thing to keep in mind, it looks like, is make sure that you specify your interpreter in each cell right now. When I wasn't doing this yesterday, there's a way to reorganize your interpreters, but it was defaulting to Spark 1 and filling up a queue and nothing was running. So we'll give this another second to run since I've got a lot of stuff running in the background here. And let's see, I can actually turn off NiFi so that we can free up some cycles, hopefully. So we'll let that keep running and we'll come back and hopefully it'll have processed. So the next cell here is basically now taking the files that we generated. So you can do just an asterisk and it'll pull in all CSV files. There we go. So if you upload, if you wanted to, so if you didn't have NiFi running and you just want to do the visualization, you've got the notebook. If you upload that generated data CSV to HDFS through Ambari, so if you do Ambari files view, you can upload the CSV. You should be able to do the same stuff we're doing here without needing to do all of the other steps. So once we've picked the files that we want, the next thing that we're going to do is go through and read our text file, and we're going to read in each line. And we're going to do a split on commas so that we can go from our comma-separated file to a what they call a resilient data store, which is basically how data is stored within Spark. And then we're going to convert that to a data frame. So we're going to parse out our dates, convert them to milliseconds, and divide by 1,000 so that we can do our turnaround times. Attribute 4 is our lab value, so we're going to convert that to a double since all of the ones that we have in here right now are numeric. And when we run that, that should basically load in all of our CSV data into a data frame. Once you have your data frame, doing your data frame name, in this case labdf.show, will show your first, I think it's like 20 or 25 records. If you put a number in there, so .show 100, that'll show the first 100 records. And that'll just give you a quick summary of what your data actually look like. So here we can see again that we're now parsing everything out nicely into our data frame. We've got all of our timestamps as seconds. We've got our component names, values, and everything else. Now to be able to do some graphing, the easiest way within Zeppelin is to convert your data frame to a table. So we're going to register a temp table, which is just data frame, register temp table with whichever name you would like to pick. In this case, I did lab data. And then something that's more familiar to most people is we can now jump into basically writing SQL and automatically graph our results. So when you do %SQL, that will use our SQL interpreter. And if you do something that has basically an X and Y, Zeppelin will pop up this graphing interface, so you don't even have to do like matplotlib or what you would do with Jupyter. So here what we're going to do is select our observation timestamp, count 1. So this is basically just going to give us a lab volume, so how many of all of our labs per time of creation. And this is just going to pop up. So all of our data is fake generated, but this is basically saying at this timestamp, there were 2 lab results in the system, this another 2, and so on. So just a quick way to look at what do kind of volumes look like over time. The next one that we're going to do is just selecting our lab component names. So basically, how many of each result do we have? We aren't doing a ton of randomization here, so all of our CBC and BMP components should basically be equal numbers between them or close to. So here we can see now we've got bicarb, BUN, chloride, creatinine, and so on. And if you hover over them, you get the number of how many of each one are in the system. We still have some processing in the background, it looks like. So now the last couple things we'll get into actually do a little bit slightly more advanced Spark just to kind of show you the features. And what this will do is we'll look at calculating turnaround time and then doing a quick moving average of the actual lab values. So we're going to switch back to our Spark 2 interpreter, and we're going to make a new data frame called turnaround time data frame, or TAT data frame. From our initial data frame, labdf, we're going to say that we want to add on a column. So doing .with column basically adds a column to this new data frame. So it'll take all of our old data, add a new column, and then what you put in the second part is actually if you want to specify some sort of equation or some sort of process. So you could say I want a static value, and that would populate everything. So if we just said 1, it would put 1 into every row of that new column. Here what we're saying is from our old data frame, take the OBX timestamp and subtract the observation timestamp. So this should basically be the number of seconds from the time of result compared to the time of order. And then we're going to register that as a new data frame. And I'm actually also going to add a show just so that we can see what it looks like here. So you can see compared to our last data frame, we added on a column, and that is just the math doing the difference between those two timestamps. That's in one of our SQL tables, so now we can say name. Let's do the average of the turnaround time and group by test name. So here should now give us turnaround time by component. And so if we look at these, we can see that on average, our CBCs are taking about 15 to 1600 seconds to result, while all of the components from our basic metabolic panel, which is a slightly faster test, take about 900 to 1,000 seconds to come out. So again, by doing this, you can put together your analytics pretty quickly. It doesn't necessarily give you fabulous detailed graphs. You know, if you spend a lot of time, you can definitely get there. One nice feature is you can set these to run on a cron job, so if you want them to auto-refresh, you can set a scheduler where you'll rerun through the cells and recreate data, so it does make it nice for being able to do quick dashboarding. So the last cell here is the most complicated one that we have, which will now go through and generate a moving average based off of the lab values that we actually saw. So switching back to Spark 2, we're going to import our windowing library, which will let us window and go through it. We're going to set our partitions, and basically this is saying that we want to do a moving average of the value plus minus 5 rows. And then like we did last time, we're going to do this lab data frame. We're going to add a new column called moving average, and that's going to be the average of the value field. So average of the value field over that specification that we did up above in Spec 1. So it's going to do that column plus and minus 5 values in the row order. And then we could do that over all labs, but that would be kind of meaningless, so we're going to filter this to a single lab, the one called chloride. We'll register a temp table and look at the output. So here now we can see that our moving average is moving along. And if we graph those down below, what we're going to do is, one thing is since we've got lots of lab values, some of which are at the same time, instead of doing this just by time, we're just going to order by time and then generate a random row number so that we don't have everything globbing up the moving average over the course of the x-axis. So if we run this, we'll see that the dark blue line is our actual values. So starting at the first value that we had in, our chlorides are largely between 95 and 110 with a few outliers. And if we look at our moving average instead in the lighter blue line, we can see that's a much tighter line, as you would expect. And from that, you can do any other stats or analytics that you would want. So. Okay, so we'll just go through and wrap up a couple of other slides, and we'll stick around. Like I said, there's a few of us to answer questions if you have them at the end. So just to look at what we went through and built today, we started off with our Python script to generate data and pushed that over to Kafka, ingested with HDF, stored in HDFS, and then did our analysis with Spark and Zeppelin at the end. Just to look at what this actually looks like in our production data warehouse, so we are doing this on our within Yale New Haven, and we use this for some dashboarding and advanced analytics. Data Innovations is our integration engine, and Epic Beaker is our laboratory information system, and then Cloverleaf is the other integration engine that we use between those. All of the data from those systems comes into one of our custom little applications for some security and data parsing reasons. We push that across to Kafka, process it with NiFi, and then one thing that we do is because we have a combination of a need for doing both batch analysis as well as real time, we store that in HDFS and then also copy that subset of that over to Elasticsearch. And for that real-time stuff in Elasticsearch, what we actually do is some Kibana dashboards so that, much like the data that I just showed you in Zeppelin, we can actually do in Kibana and look at our lab turnaround times, volumes, and all of these are interactive and clickable. So if we click on this is which lab the test was performed in the middle, so we can say, show me labs and turnaround time for only those at Yale New Haven main lab versus Shoreline or one of our other outpatient labs, and the rest of the data will update in real time, including the turnaround times, outstanding orders, volumes, and so on. The biggest data stream that we currently have, and again, just going to go through the architecture of this quickly, is our continuous patient monitoring. So for this data stream, we actually generate about 6 to 9 billion data points per month from all of our monitoring devices in our ERs and ICUs across our entire health system. For these, we needed something that was highly scalable, something that supported batch and real-time analytics. And when we looked at the tools that we chose, again, it's a lot of overlap, but a couple of, one key unique one, which was Storm. So our data pulls in through a similar pipeline, but instead of using NiFi, we use Storm just because we needed to scale a little bit more for what we had installed in our infrastructure. And then again, stored in HDFS and Elasticsearch for analytics. Just a little bit more detailed. So again, coming in from our different monitoring systems, in through one of those emissary services for the same security reasons, to Kafka, to Storm, and then HDFS. And then rather than doing Storm to Elastic, we actually use Spark to copy stuff over in batch it'll be scheduled every hour or so once we finalize that in production. The last thing that I wanted to look at was one of our image analysis use cases. This one's much lower volume, but what we have is a newer instrument that does the CBCs, but also does what we call a peripheral blood smear. So it takes a small drop of blood, puts it on a glass slide, smears it out so that somebody can look at it under a microscope. A fairly inefficient process for actually doing diagnostics and not really that quantitative. So what we started developing is a pipeline where we can actually ingest those images with HDF, store them in HDFS, and then we actually have some machine learning libraries we've built in-house that does the image recognition for us. So HDF will trigger off the machine learning algorithm to give us our evaluation, and then we store the results, metadata, and features in Elastic with Spark analysis. So just in conclusion, having an analytic plan in place before you start capturing and ingesting your data is good, but not always possible. If you don't have that in place, definitely try to identify the key pieces of data that you might be able to extract and filter on before just dropping everything completely unstructured. When you can, it'll definitely save you some time in the future. The data science ecosystem is definitely complex. Even today, we've talked about no less than probably about 10 or 15 different tools and packages. It's complicated, it takes time to learn, but it can be done. Just go through it and again, find some of those key applications where you can reuse them between pipelines. So, between the laboratory data workflow and the image analysis workflow, we reuse a lot of those components and even the code. So our HL7 receiver up that we do in our little custom emissary app, that's the same for all of our HL7 feeds. We don't have to reprogram it, we just add on another port number for new feeds. And the data processing pipelines are similarly complex. So again, when you can reuse those architectural patterns and code, will definitely help save time if you're pulling in a large number of different data sources. So thank you all for coming and sticking around. If you have questions, Carolyn and Will are over here, Tommy over on this side, or feel free to come up and chat with me. Our email address is if you have any questions. And again, GitHub has all of the code, and I'll upload the presentation later today so that you have the other instructions if you want it. Thank you.